So today is the actual last day of the semester before the final exam. And the last problem we had on the last quiz, we only had one problem. Now, if you didn't have the divergence theorem, this problem here would be actually quite difficult. So my F is xy squared plus 3xz squared, x squared y plus the x squared y plus, oh, I got it right, plus y cubed, and then 3x squared z minus z cubed. Okay, now what makes this one work is that our surface is closed. We are bound we're bound by the great toilet paper roll, if you want to call it that, because that's exactly what's going on here. We're bound by, let's see, z equals -2 and z equals 4. So that means on the xz plane, or excuse me, the xy plane, we would be a little bit, okay, this would be a little bit below, a couple units below, this would be 4 units above. We're also bound by the circular cylinders, the outer one being x squared plus y squared is 36, the inner one being x squared plus y squared equals 4. So that means, because I'm asking you for flux, that's what this represents, you would have to consider all the surfaces. And all the surfaces are not only the outside surface, the top surface and the bottom surface, but you'd also have an inside surface. Yikes. And the normals would be pointing in different directions. Although none of the surfaces would be terribly demanding, you have 4 separate flux integrals you'd have to calculate. That's a lot of work. But because this is a closed surface, we can use the divergence theorem. So the first thing we're going to do is say, oh, pen just skipped here. The divergence of F, remember the divergence of F is essentially dotting the vector with the partial. So I'm taking the partial of the first, adding it to the partial of the second, adding it to the partial of the third with respect to x, y, and z. So the partial with respect to x would be y squared plus 3z squared. With respect to y here would be plus x squared plus 3y squared. And then with respect to z would be plus 3x squared minus 3z squared. And I notice that those guys cancel, and I'm left with 4x squared plus 4y squared. Well, that's a very, very friendly integrand, so I'm going to go put it back up here. Oh my goodness, I have a lot of residue on my board today. So that means that this would be the triple integral over the volume of 4x squared plus 4y squared dv. Now, clearly, because my boundaries are circular in nature in the xy plane, I would want to go with cylindrical. Definitely do not want to do spherical coordinates. There's nothing spherical about either the region or the integrand. So if we go with cylindrical coordinates, then I have a lot of circular things going on here. And this would then become, let's see, in the, so I'm 0 to 2 pi for the theta. I had, remember, a circular cylinder where the inner circles were of radius 2 and 6. And then I had the z's going from -2 to +4. This in polar would then be 4r squared. And then I'd have r dz dr d theta. So let's just go ahead and make that 4r cubed. Now, when I integrate this, the integration should be pretty low level at this point. This should not be something terribly taxing. Oops. 2 to 6, and then here 4r cubed. So I would be 4r cubed z from -2 to 6 dr d theta. Go ahead and mute yourself. So z is 6 and z -2. Okay. So as I'm doing the z, is that 6? Did I have that right? 6 in. Oh, I'm sorry. Not 6 and negative. Hold on. Did I write the right z's down?
Z is -2 to 4.
-2 to 4. I'm sorry, I was copying down the other guy. Sorry about that. Yeah, I have it right here. So Z of 4 minus Z of -2, that'd be 6. So that's just going to be 24r cubed dr d theta. So now integrating that, 0 to 2 pi, I would have 6r to the 4th from 2 to 6 d theta, which would be, so 6 times, let's see, what does that give us? That gives us 7,680 d theta, running through my calculator. And my final answer will be this times 2 pi, so 15,360 pi. I know Josue was suspicious of that last ASIC because it was so large. Well, actually, the force vector is dealing with things raised to powers, and I have fairly large shapes. So there's really no knowing, what is big, what is small. You just navigate through. What we like about this one, again, the original problem was horrible, but because I could use divergence theorem, much the same way as using Green's theorem made line integrals generally much simpler. So this is fair game. Stokes's theorem is fair game. Flux is fair game. All of these are fair game. Now, they won't all be on the exam, but you should certainly expect some of them. Now, the final exam, as I mentioned last week, there's going to be 14 questions spread throughout the course. You're going to do 10 of them. Now, the thing is, you don't have to give me 10 great answers. You got to give me 5 or 6 great answers and then get through a few more. If you want an A, yeah, you're going to have to give me 7 or 8 probably perfect answers and then a couple that are really, really good. But if you're just trying to get through the final, again, you want to get a few of them very right. And then the rest of them, you can kind of muddle through because everyone thinks it as all or nothing. No, they're not all or nothing. In this problem here, if you got it to here, right there, that line right there is probably 60% of the credit of this problem because the integration of the problem is not high level. It's translating it into the statement that's the key. So again, everything's fair game. I will be doing the same thing, and I will be sending you an email tomorrow to remind you, but I'll send you the final a few minutes early so you have time to print it out. I'll send you the Zoom link so everybody gets on. And of course, if you're not going to take the final, you've already emailed me or you're going to email me, so I don't wonder where you are. I'm not worried about you, right? If something comes up, I just had a student email me right before the class, it was a different class, and they said, I'm not going to take the final because it's not going to matter. And then I looked and said, they're right. They'd actually had a 0 on all 3 exams. This is a different calculus class. It's a person who didn't come to a single lecture. They admittedly speaking, they didn't buy the book. They said their internet wasn't good, so they rarely logged on to Canvas. They went the whole semester. I think they turned in a couple of quizzes. And that was the whole semester. Yeah, so they're not going to take the final. That probably makes sense. Not really sure why they took the course. In 4 months, they turned in 2 quizzes and got 0 on one of them, and I give them partial credit on the other. So they wouldn't be the first person to ever end the course with a grade of 0. I wanted to make sure they got at least a couple of points, participation trophy, that kind of thing. And I had, by the way, multiple people in that class with over 100% averages. So I'm not really sure what the disconnect was, but in this class here, those who are going to take the final, you're going to take the final because it's going to accelerate your cause. And I keep getting asked the same question over and over again, even though I put it in the syllabus and I mentioned it out loud. The final will replace your lowest exam and 6 lowest quizzes if it is better than them. If it is not, then it won't. The final only counts if it exceeds those other scores. So you can't lose anything by taking the final, you can only gain. And if it's reasonable that you can get the grade you want. And at this point, because the last quiz is done, everybody in here can easily now go to Canvas, put the cursor on the quiz total, so you can see your total for the quizzes, and then manually go through, okay, which are my 6 lowest? And then go to the exams. Well, that's easier. What's my lowest exam? Now, go to the total on Canvas and subtract those 6 quizzes and exam from your total. Now that's your sort of naked score before you get to the final. Now you just got to look at what's the gap that I need to raise my grade. How much better does the final have to be than my previous scores? And if you have one poor exam, you may not have to do that great on the final to raise your grade. So that's one of the benefits of this grading system. Now, I think everything's pretty clear. We've gone over this a couple times. what you need to do. So hopefully everybody's prepared mentally. Now the rest is just practicing. So I will stop now.